Okay, in this problem we have this tall pole right here that's 3 meters tall, and we're applying a 400 Newton force a half a meter off the ground, so the pole is on the ground. We're given the mass of the pole, that it's 100 kilograms. We're given the moment of inertia, which is 75 kilogram meter per second squared, and we're given the coefficient of static and kinetic friction, which is 0.3 and 0.25 respectively. And we want to figure out what the angular acceleration of this pole is. So our first step, like always, is draw a free body diagram and draw a kinetic diagram. In our free body diagram, we're going to identify all the forces that are acting on the pole. And in our kinetic diagram, we are going to identify all of our accelerations. So since this pole is on the ground, we know we're going to have a normal force that points straight up, and we're going to have a weight that acts through our center of gravity. And our center of gravity is at point G. So here's our weight. Our weight is going to be equal to our mass times gravity. And gravity is 9.81 meters per second squared. So 100 times 9.81 is going to be 981 newtons. Now, since we're pulling with a 400 Newton force, let's write that in. And we have to identify our frictional force. So we're pulling this way. Our frictional force is going to want to oppose our direction of motion. So here's our frictional force, and here's our 400 Newton force. Now what we don't want to do, we do not want to say that our frictional force is equal to our coefficient of static friction times n, or our coefficient times of kinetic friction times n. We don't want to do this, so we do not want to take that step like we do in some other problems because of the type of motion this is under. So now this is our free body diagram. We want to draw our kinetic diagram, and our kinetic diagram is going to have an acceleration in this direction. So this is going to have an acceleration towards the right. This is its center of mass. So its mass is 100. So we have 100 AG, which is completely horizontal. Now we're also going to say it's going to fall this way. So the acceleration of the center of mass and its angular acceleration, the directions of these work together. So we're going to say that this is falling in the in the clockwise direction, and this is being pulled towards the right. So our directional, for convenience, our coordinate system, x is going to be this way, y is going to be this way. Our acceleration of our center of mass is going to be in our positive direction of x, and our positive direction for acceleration is going to also be clockwise. Now, what we want to do is we want to use our equations of motion. So we want to take the sum of the forces in the x direction. We want to equal this to a mass times an acceleration in the x direction. We want to take the sum of the forces in the y direction, equal to a mass times an acceleration in the y direction. And we want to take the sum of the moments about point G, which is our center of mass, and this is going to be equal to our moment of inertia about our center of mass times our angular acceleration. So if we take our sum of the forces in the x direction, again, the right is positive, we're going to have 400, this 400 Newton force, minus our frictional force. And again, we are not substituting in the coefficient of friction times our normal force at this point. So this is going to be equal to our mass times acceleration in our x direction, which is 100 times the acceleration of g. Our sum of the forces in the y direction, it's going to be positive is up. It's going to be a minus 981. plus NA, so our normal force, which is equal to 0 because there's no acceleration in our y direction. So here we get the normal force NA is equal to 981. And finally, we're going to have the sum of the moments about point G. Point G is the center of mass right here, and is equal to our moment of inertia about our center of mass times our angular acceleration. But look, this normal force goes right through our center of mass. Our weight goes right through our center of mass. So the only two forces that have any moment on our system is this 400 Newton force that we're applying and this frictional force. And this is the way we said is positive. So if we rotate our frictional force, our normal, if we rotate this 400 Newton force that way, it wants to go tail first, so it's going to be a minus 400 times the perpendicular distance. The perpendicular distance, we know this is 0.5. We know our this is directly in the middle. This is 1.5 feet from the ground. So this distance from here to this 400 Newton force is just going to be 1 meter. So it's going to be minus 400 times 1. Now this frictional force is going to be positive because it's going, the arrowhead is going first. So it's going to be a plus frictional force times this entire distance, which is 1.5. And this is equal to our moment of inertia about our center of mass, which is given for us. So it's 75 times our angular acceleration. Now, we still have 3 unknowns. We don't know what this frictional force is. We don't know what our acceleration of our center of mass is. And we don't know what our angular acceleration is. But we only have 2 equations to work with because the sum of the forces in the y sort of it's doing its own thing. It's just finding out the normal force. So we have 2 equations, this one, and 3 unknowns. But that's okay. We're going to assume that this does not slip. So we're going to assume no slipping. And because we assume no slipping, we're going to say that the acceleration of the center of mass is going to be equal to our angular acceleration times r. And r is the distance, oops, I think I moved the screen. R is the distance is the distance to the center of mass. So for us, it's going to be this 1.5 meters. It's going to be from the ground to the center of mass, which is 1.5. So this is going to be equal to 1.5 alpha. So we can substitute this right here back into this equation, and we can move this 400 over to this frictional force over to the other side. We can get this equation in terms of the frictional force. So if we do that, we get the frictional force is equal to 400 minus 100 times this 1.5 alpha. Now, since we have this expression for our frictional force, we can, let's just star that, we can substitute this right here. So we can put our new expression for frictional force into this equation right here. And when we do that, minus 400 plus this 400 minus 100 times 1.5 alpha times this 1.5. So I just substituted in my frictional force right here is equal to 7.5 alpha. And now we have one equation just in terms of our angular acceleration. So we can solve for our angular acceleration, and we can get our angular acceleration is equal to 0.667 radians per second squared. Then we can put this 0.667 back into this equation right here, and we can get that our frictional force is equal to 300 newtons. And we can, if we really wanted to, even though the problem doesn't ask it, we can figure out what our acceleration of our center of mass is by using our 300 newtons of frictional force right here, and we can get our acceleration of our center of mass is equal to 1 meter per second squared. Okay, this is great, except now we have to check if our assumption that this doesn't slip is true. So in order to check that assumption, we say our frictional force is less than or equal to the coefficient of static friction. So mu s times the normal force. We have our normal force right here. So is our frictional force 300 less than or equal to 0.3 times 981? Well, if you do this multiplication out, you get this is equal to 294.3. So 300 is not less than 294.3. So this is not true. In this case, so our assumption of slipping was not correct. We have to now say that our frictional force is equal to this coefficient of kinetic friction times our normal force, which I called NA. So this is going to be equal to 0.25 times 981, and this is equal to 245.3 newtons. And now we just have to go back. We can plug this straight into this equation, and we can find what our new acceleration of our center of mass is. So we can just, it's not as tough going back and resubstituting these numbers in. So we get our acceleration of our center of mass is equal to 1.55 meters per second squared. And we can go to this equation right here, and we can plug in our new frictional force. So this frictional force right here is going to be this 245.3, and we can solve for alpha. And what we're going to get is that alpha is going to be equal to minus 0.428 radians per second squared. Now what does this tell us? This tells us this minus sign means it's not going in this direction that we defined our positive alpha to be in, our positive angular acceleration. It's going in the counterclockwise direction. So alpha is equal to 0.428 radians per second squared in the counterclockwise direction.